Students, welcome to my second video on Chapter 9, Hydrogen. In this video, I'll be explaining about water, its physical and chemical properties, its structure, about hard and soft water, methods to remove hardness of water, and about hydrogen bonding. Now, shall we learn about water?
Water is essential to all forms of life. A major part of all living organisms is made up of water. Human body has about 65% water, while some plants have as high as 95% water. It is a crucial compound for the survival of all life forms. So, it is a solvent of great importance. However, distribution of water over Earth's surface is not uniform. The estimated world water supply is shown in the table displayed. Now students, did you notice this? Quantity of water available from rivers all over the world is 10% less than the quantity of water that is available in our atmosphere as water vapor. Quite interesting, right? Shall we now look at the physical properties of water? We all know water is a colorless and tasteless liquid. Students, remember hydrogen bonding, which you have learned in the chapter on chemical bonding? In that, you should have learned that water molecules exhibit hydrogen bonding. Presence of extensive hydrogen bonding between water molecules is the reason for most of the unique properties exhibited by water in the condensed phase. That is, when it is in the liquid state and when it is in the solid state. Okay, so and remember, water is a hydride of oxygen which belongs to 16th group. Okay, henceforth, the freezing point, boiling point, heat of vaporization and heat of fusion values of water are higher than those of the hydrides of elements of the same group such as hydrogen sulfide, hydrogen selenide, hydrogen telluride and so on. Now what is the reason? The reason is that it is due to the presence of hydrogen bonding in water molecules which is absent in other hydrides of the group. Okay, hydrogen bonding is absent in hydrogen sulfide, hydrogen selenide, hydrogen telluride. Why is it so? Because hydrogen bonding occurs between hydrogen atom of one molecule with either nitrogen, oxygen or fluorine atoms of other molecules and not with any other atom. Since hydrogen bonding is absent in hydrogen sulfide, hydrogen selenide and hydrogen telluride, their freezing point, boiling point, heat of vaporization and heat of fusion values are lower than those of water. Students, this is a very important point. You may get a question based on this in your exam. So, give importance to this point and learn. In comparison to other liquids, water has a higher specific heat, thermal conductivity and surface tension. All these properties allow water to play a key role in the biosphere. For example, the high values of heat of vaporization and heat capacity of water are responsible for moderation of climate and body temperature of living beings. Remember, why are the values of heat of vaporization and heat capacity of water high? It is due to hydrogen bonding in water molecules. Okay, now water is regarded as a universal solvent. Why? Water is an excellent solvent for transportation of ions and molecules required for plant and animal metabolism. For instance, if you take photosynthesis, the process in plants that create sugars for all life forms, it requires water. Water facilitates the transportation of molecules like oxygen, which is very, very essential for respiration, without which we are dead. Clear? So, water is an excellent solvent for transportation of ions and molecules required for plant and animal metabolism. Okay, inorganic substances are mostly ionic and they dissolve readily in water. For example, if you take salt, which is NaCl, sodium chloride, and if you put it in water and stir it, what do you observe? It dissolves readily. Clear. So inorganic substances being mostly ionic, they dissolve readily in water. Also, covalent organic compounds like alcohol, carbohydrates, for example sugar, and so on, they dissolve in water due to their ability to form hydrogen bonds with water molecules. Clear. Now, why do organic compounds like alcohol, sugar, and so on, they dissolve in water? It is due to their ability to form hydrogen bonds with water. Since water can dissolve various substances and is widely used for preparing so many solutions, it is a universal solvent. Chemical properties of water. Water reacts with a large number of substances, so it displays a wide range of reactions. It behaves as an acid, as a base, as an oxidant, as a reductant, and as a ligand to metal ions. Now let us first look at the amphoteric nature, that is acid-base character of water. Water has this ability to act as an acid as well as a base. Okay, it can behave both as an acid and as a base. For this reason, it is said to be amphoteric in its character. Now, how will water behave in the presence of a base which is stronger than itself? In the presence of a base which is stronger than itself, water will behave like an acid. Clear? Now look at the reaction between water and ammonia. Ammonia is strongly basic in character in comparison with water. So in the presence of a stronger base, water will act as an acid. Okay, water reacts with ammonia to give OH minus hydroxide ion and ammonium ions. Clear. Now how will it behave when it is present near an acid which is stronger than itself? In the presence of an acid which is stronger than itself, water behaves like a base. Okay, now for example, look at the reaction between water and hydrogen sulfide. Hydrogen sulfide is strongly acidic in nature in comparison with water. So in the presence of such a strong acid, water will act as a base. Okay, so water reacts with hydrogen sulfide to give hydronium ion and Hs minus ions. Okay, in the presence of a strong acid like hydrochloric acid, water behaves like a base. Okay, so water reacts with hydrochloric acid to give hydronium and chloride ions. Okay, let us look at autoprotolysis. It means self-ionization of water. Since water is a weak electrolyte, it undergoes ionization to a very small extent to give hydronium and hydroxide ions. This is called autoprotolysis or self-ionization of water. During the self-ionization of water, one of the water molecules behaves like an acid and the other water molecule behaves like a base. They undergo self-ionization to a very small extent and lead to the formation of hydronium ion and hydroxide ion. This process is called self-ionization of water, technically called autoprotolysis of water. Now the second chemical property associated with water is redox reactions, in the sense oxidation reduction reactions. With reactive metals, that is highly electropositive metals like sodium, potassium and so on, water acts as an oxidizing agent. So water acts as an oxidizing agent with very reactive metals like sodium, potassium and so on. Okay, so water reacts with sodium to give sodium hydroxide plus hydrogen. Okay, in this reaction, water is reduced easily to hydrogen. Okay, so here it acts as an oxidizing agent. So water is a great source of hydrogen. In the presence of an electronegative element, water behaves like a reducing agent. And what is a reducing agent? A reducing agent is a substance which reduces another substance and gets oxidized during the reaction. Now look at the reaction happening between fluorine and water. We know fluorine molecule is an electronegative molecule. Okay, so in the presence of an electronegative fluorine molecule, water acts like a reducing agent. Water reduces fluorine molecule to hydrogen fluoride and gets oxidized easily to oxygen. Okay, Now look at what happens during photosynthesis. Water acts as a reducing agent. So water reduces carbon dioxide and gets oxidized easily to oxygen. Okay, now the third chemical property associated with water molecules is that it undergoes hydrolysis reactions. Because of its high dielectric constant, water has the ability to dissolve most of the inorganic ionic compounds. Okay, that is, it has a very high hydrating tendency. Okay, why water possesses a very high hydrating tendency? Because of its high dielectric constant value. Due to its high dielectric constant value, water can dissolve most of the ionic compounds. Okay, certain covalent compounds are also hydrolyzed by water. So what do you mean by hydrolysis? Decomposition of a compound by whom? By the action of water is called hydrolysis. Many compounds are hydrolyzed, in the sense decomposed by water. During hydrolysis, the H plus and OH minus ions of water interact or react with the anions and cations of the compound undergoing hydrolysis respectively, leading to the formation of either an acid or a base or both. Here are a few examples of hydrolysis reactions leading to the formation of acid as products. When phosphorus pentoxide undergoes hydrolysis by water, the H plus and OH minus ions of water react with the respective anion and cation of phosphorus pentoxide molecule, leading to the formation of phosphoric acid. Okay, so water decomposes phosphorus pentoxide molecule to phosphoric acid. Clear? Now, in the hydrolysis of silicon tetrachloride by water, the H plus ion of water reacts with the chloride ion of silicon tetrachloride molecule, and the OH minus ion of water reacts with Si4 plus, silicon 4 plus cation of silicon tetrachloride molecule, leading to the formation of silicon dioxide and hydrochloric acid. And this is an example for the formation of base as a product due to the hydrolysis of a nitride by a water molecule. Okay, in this reaction, the H plus ion of water molecule reacts with nitride ion, leading to the formation of ammonia as a product. Okay, so that's how an acid or a base is formed as a product due to the decomposition of a compound by water. Okay, due to the hydrolysis of a compound by water. The fourth important chemical property associated with water is hydrate formation. Many ionic compounds crystallize from water, and when they do so, one or more water molecules may be associated with them in their crystal structure. Okay, examples of hydrates are barium chloride dihydrate, copper sulfate pentahydrate, and so on. You can see that in barium chloride dihydrate, two water molecules are associated with the ionic compound in its crystal structure. Now, in copper sulfate pentahydrate, 5 water molecules are associated with the copper sulfate's crystal structure. So this water in combination with ionic salts is called water of crystallization, and such crystals are called hydrated salts or simply hydrates. Okay, hydrates are classified into three. They are coordinated water hydrates, interstitial water hydrates, and hydrogen bonded water hydrates. Let us now try to understand what coordinated water hydrates are. These are hydrates in which the water molecules are coordinated to the central metal ion to form complex ions. That means the water molecules in coordinated water hydrates are linked to the central metal ion by means of coordinate bonds. Okay, such hydrates are called coordinated water hydrates. Examples are chromium chloride hexahydrate, nickel nitrate hexahydrate, and so on. Okay, let us look at chromium chloride hexahydrate example. In chromium chloride hexahydrate, the 6 water molecules are linked to the central chromium ion by means of coordinate bonds. Okay, so chromium chloride hexahydrate is an example of coordinated water hydrates. Now we move on to interstitial water hydrates. These are hydrates in which the water molecules are present in the interstitial sites or voids of the crystal lattices. Okay, what do you mean by interstitial sites or voids? Okay, interstitial sites or voids means vacant spaces or holes which are present in between the positive cations and the negative anions of the crystal structure of ionic compounds. Okay, an example is barium chloride dihydrate. In barium chloride dihydrate, where are these two water molecules present? Where do they occupy in the crystal structure of barium chloride? They occupy the vacant spaces which are present between the barium and chloride ions of the barium chloride crystal structure. Okay, so barium chloride dihydrate is an interstitial water hydrate. Okay, now we move on to the third category, which is hydrogen bonded water hydrates. These are hydrates in which the water molecules are linked to some oxygen containing anions by hydrogen bonding. Okay, an example is copper sulfate pentahydrate. In copper sulfate pentahydrate, out of the 5 water molecules, 4 water molecules are linked to the central copper 2 plus ion by means of coordinate bonds. Okay, while the 5th water molecule is linked to the sulfate ion by hydrogen bonding. Okay, so for this reason, copper sulfate pentahydrate may be represented as like this. Okay, here the 4 water molecules which are linked to the central copper 2 plus ion are placed or enclosed inside the coordination sphere. Okay, this is called coordination sphere, square brackets. So, this means the 4 water molecules of copper sulfate pentahydrate are linked to the central copper 2 plus ion by means of coordinate bonds, while the 5th water molecule is linked to the anion, sulfate anion of copper sulfate by means of hydrogen bonding. Okay, that is why we have placed these out of the coordination sphere. Now, you may get a question like this. How many hydrogen bonded water molecules are associated in copper sulfate pentahydrate? So, how many copper water molecules are associated by hydrogen bonding in the case of copper sulfate pentahydrate? Only one water molecule is associated to the anion by hydrogen bonding in copper sulfate pentahydrate. Okay. Having learned about the physical and chemical properties of water, let us now look at the structure of water. In the gaseous state, water exists as a bent molecule. Okay, it has a bond angle of 104.5 degrees and the bond length of each of these OH bonds is the same, that is 95.7 picometers. Water is a highly polar molecule due to the high electronegativity of oxygen atom. Students, water molecule as such is a neutral molecule. But see, charge separation occurs in water molecule. As a result, it is highly polar. Why is it highly polar? It is due to the high electronegativity of oxygen atom. Clear? What is the tendency of an electronegative atom? It has the ability to attract the shared pair of electrons towards itself. Okay, we know oxygen is the second highest highly electronegative element in the whole of the periodic table. So it has greater tendency to attract the shared pair of electron towards itself. Okay, the electronegativity of oxygen is much higher than that of hydrogen atoms. So the shared pair of electrons in the OH bonds are attracted slightly towards the oxygen atom. So the electron density here will shift towards oxygen atom. As a result, oxygen carries two partial negative charges characteristic of these two hydrogen atoms, and each hydrogen atom carries a partial positive charge. Okay, so that is why water behaves as a highly polar molecule. This is the orbital overlap picture in water molecule. It tells you how water molecule gets this bent shape. In water molecule, the central oxygen atom is sp3 hybridized. So, it has 4 sp3 hybrid orbitals. 2 out of 4 sp3 hybrid orbitals of oxygen are half filled. Okay, and hence they overlap with the oneness atomic orbital of these two hydrogen atoms. When these sp3 hybrid orbitals of oxygen atom overlap with the oneness atomic orbital of hydrogen atom, they overlap axially. Okay, end-to-end overlapping occurs. As a result, sp3s sigma bonds are formed. That is, OH sigma bonds are formed in water molecule. The remaining two sp3 hybrid orbitals don't take part in bonding, so they remain as lone pairs of electrons. Okay, since oxygen atom is sp3 hybridized, the geometry of water molecule is expected to be tetrahedral. Okay, we know for a tetrahedral molecule, the bond angle should be 109.5 degree. But experimentally, in water molecule, it has been found that the actual HOH bond angle is 104.5 degree. Okay, we expect the angle to be 109.5 degree, but actually it has been found that the HOH bond angle, okay, this bond angle in water molecule is 104.5 degree. This may be explained on the basis of VSEPR theory. Okay, in water, the oxygen atom is surrounded by two shared pairs and two lone pairs of electrons. And we know the lone pair repulsion is greater than lone pair bond pair repulsion, which in turn is greater than the bond pair repulsion. As a result, the HOH bond angle in water is slightly smaller than the regular tetrahedral bond angle of 109.5 degree. Clear? So this is how water gets its bend shape. In the liquid state, water molecules are held together by intermolecular hydrogen bonds. See, this picture shows the association of water molecules by hydrogen bonds. Okay, each water molecule is associated to other water molecules by means of hydrogen bonds. Okay, for this reason, liquid water has high boiling point. Due to this extensive hydrogen bonding in water molecules, liquid water has high boiling point, which is 373 Kelvin or 100 degrees Celsius in the Celsius scale. Okay, the crystalline form of water is ice. At atmospheric pressure, water crystallizes in the hexagonal form. At very low temperature, it condenses to cubic form. Students, this is for your information. Now we'll look at first case. Why ice floats on water? Ice floats on water because density of ice is less than that of water. Due to extensive intermolecular hydrogen bonding between water molecules, ice gets an open type structure like this with wide holes. Clear? And this is why ice floats on water. These holes can hold some other molecules of appropriate size interstitially. And do you know that ice formed on the surface of a lake in water season provides thermal insulation? This ensures the survival of aquatic life and is of great ecological significance. Now let's study about the structure of ice. What is the structure of ice? It is very important, children. You should register this in your mind. Ice has a highly ordered three-dimensional hydrogen bonded structure. Okay, see in this structure, the green circles, they denote the bigger oxygen atoms and the orange circles denote the smaller hydrogen atoms. Okay, so you can see that a water molecule has an oxygen atom bonded to two hydrogen atoms, and this in turn is bonded to other water molecules by means of hydrogen bonding. Okay, X-ray studies on ice crystals show that each oxygen atom, okay, each oxygen atom here is tetrahedrally surrounded by four other oxygen atoms. See, this oxygen atom is connected to oxygen number 1, oxygen number 2, oxygen number 3, oxygen number 4. So, each oxygen atom in the crystal structure of ice is tetrahedrally surrounded by four other oxygen atoms at a distance of 276 picometers. That is, there is a hydrogen atom between each pair of oxygen atoms. So, this gives ice an open cage-like structure with wide holes. Okay, due to the presence of wide holes in the open cage-like structure of ice, ice floats on water. Its density becomes less than that of water. Clear? I now move on to the next very important topic, which is hard and soft water. Natural water contains dissolved salts. Depending upon its behavior towards soap solution with respect to lather formation, water may be classified as soft water and hard water. Water that produces lather with soap readily is called soft water. Water that does not produce lather with soap readily is called hard water. Clear? So this is the main difference between soft water and hard water. What is soft water? It produces lather with soap readily. Hard water does not produce lather readily with soap. Okay, examples of soft water are rainwater, distilled water, demineralized water. Examples of hard water are sea water, river water, spring water, well water, and lake water. Now, what makes water hard? Hardness of water is due to the presence of hydrogen carbonates, chlorides, and sulfates of calcium and magnesium. Hard water is not suitable for laundry, that is, for washing clothes. We know that hard water does not produce lather readily with soap. Here, let's try to understand why hard water fails to form lather immediately with soap. First of all, what is soap? That is detergent in this context. Soap is a salt. It is a sodium or potassium salt of certain higher fatty acids like stearic acid, palmitic acid, oleic acid, and so on. Imagine the soap that you are going to use now contains sodium stearate. What is sodium stearate? It is a sodium salt of the higher fatty acid known as stearic acid. Okay, this is the formula of sodium stearate, C17H35COO minus Na+. The anion part of sodium stearate is C17H35COO minus and the cation part of sodium stearate is Na+. Okay, so students, what is the main ingredient in the soap that you are going to use for laundry? Sodium stearate. When hard water is treated with soap solution containing sodium stearate, the calcium and magnesium ions present in hard water react with the anions of fatty acids present in soap to form scum or curdy white precipitate. See, this is the scum or the curdy white insoluble precipitate which is formed by the reaction of calcium and magnesium ions present in hard water with the anion of sodium stearate. Clear? So as a result, hard water does not produce lather with soap immediately. Therefore, it is unsuitable for laundry. Okay, so what prevents hard water from producing lather with soap? The insoluble curdy white precipitate formed by the reaction of calcium or magnesium ions of hard water with the anion of sodium stearate, okay, present in soap solution prevents the formation of lather. Now, let's look at the second case. Hard water is harmful for boilers. What is the reason? It is due to the deposition of insoluble salts of calcium and magnesium in the form of scales. Okay, due to the deposition of the insoluble salts of calcium and magnesium in the form of scales, the efficiency of boiler gets reduced. So it is harmful for boilers. Hardness of water is of two types, temporary hardness and permanent hardness. Temporary hardness is due to the presence of calcium and magnesium hydrogen carbonates. That is, temporary hardness is due to the presence of calcium hydrogen carbonate or magnesium hydrogen carbonate. Okay. Now, what is permanent hardness? It is due to the presence of soluble salts of calcium and magnesium in the form of chlorides and sulfates in water. Okay, if calcium chloride, magnesium chloride, calcium sulfate and magnesium sulfate are present in water, then the water becomes permanently hard in nature. Okay, now there are few ways to remove the temporary hardness of water. They are simply by boiling or by Clark's method. Permanent hardness may be removed not by boiling but by using washing soda, by Calgon's method, by ion exchange method and by synthetic resin method. Let's see the various methods to remove the temporary and permanent hardness of water. Now, temporary hardness of water due to the presence of soluble calcium hydrogen carbonate and magnesium hydrogen carbonate can be removed simply by boiling hard water. When boiled, the soluble magnesium hydrogen carbonate is converted to insoluble magnesium hydroxide, that is precipitated. Okay, it gets precipitated at the bottom of the container. Okay, now in this case, magnesium hydroxide is precipitated instead of magnesium carbonate. Okay, we expect magnesium carbonate as the product that gets precipitated, but on the contrary, here magnesium hydroxide is precipitated. Why? This is because the solubility product of magnesium hydroxide is high when compared to that of magnesium carbonate. Okay, now when boiled, the soluble calcium hydrogen carbonate is converted to insoluble calcium carbonate precipitate. Okay, now the insoluble magnesium hydroxide and calcium carbonate precipitates that settle at the bottom of the container can be removed by filtration, and the filtrate thus obtained will be soft water free from calcium and magnesium salts of hydrogen carbonates. Clear? So, this is one method by which we can remove temporary hardness of water. The next important method which can be used to remove temporary hardness of water is Clark's method. In this method, calculated amount of lime, that is calcium hydroxide, is added to hard water. The calcium hydrogen carbonate and magnesium hydrogen carbonate present in the temporary hard water react with lime to form insoluble calcium carbonate and magnesium carbonate respectively, which can be filtered off, and the filtrate will be a soft water. Let us now understand the methods to remove permanent hardness of water. Permanent hardness cannot be removed by boiling, but it can be removed by treating hard water with washing soda. Washing soda is nothing but sodium carbonate. Washing soda reacts with the soluble chlorides and sulfates of calcium and magnesium in hard water and converts them into insoluble carbonates, which are precipitated, and they can be filtered off easily. See, magnesium chloride, which is a soluble salt in hard water, reacts with washing soda and results in the formation of magnesium carbonate, which is an insoluble precipitate. We can remove this by filtering it off. Okay, now calcium chloride reacts with sodium carbonate, giving calcium carbonate and sodium chloride. Calcium carbonate can be easily removed by filtering. Now magnesium sulfate and calcium sulfate, when they react with sodium carbonate, they lead to the formation of magnesium carbonate and calcium carbonate respectively, and they since they are precipitated, they can be easily filtered off. The resulting filtrate will be a soft water. The second method to remove permanent hardness of water is Calgon's method. What is Calgon? It is sodium hexametaphosphate, Na6P6O18. Okay, this is the chemical formula of Calgon, and Calgon is the commercial name of sodium hexametaphosphate. When hard water is treated with Calgon, the calcium and magnesium ions present in it combine with sodium hexametaphosphate to form soluble complexes of calcium and magnesium salts. Okay, this is the soluble complex anion. Okay, here M stands for calcium or magnesium ion. The complex anion so formed keeps the magnesium and calcium ions in solution. Okay, in other words, we can say simply that Calgon arrests calcium and magnesium ions. Okay, they are now in the custody of Calgon. Since Calgon forms soluble complexes of calcium and magnesium ions, the calcium and magnesium ions are made ineffective. They are now not free to react with soap, and as a result, they do not form any insoluble precipitate with soap. Hence, hard water treated with Calgon is rendered soft, which in turn produces lather immediately with soap solution. The third method for the removal of permanent hardness is ion exchange method. It is also called as zeolite or permutate process. What is a zeolite? Hydrated sodium aluminum silicate is called a zeolite, in other words, permutate. It is represented as NaAlSiO4 into X times water. For simplicity's sake, it can also be written as NaZ. Okay, now when zeolite is added to hard water, it exchanges its sodium ions with calcium and magnesium ions of hard water. In this reaction, M2 plus represents calcium or magnesium ions. Okay, now when zeolite has exchanged all of its sodium ions with calcium and magnesium ions of hard water, it gets exhausted. The exhausted form of sodium zeolite is written as Mz2, where in place of sodium we have M. M stands for calcium or magnesium. Okay, now it is possible to regenerate an exhausted zeolite by treating it with aqueous sodium chloride solution. What happens is that the exhausted zeolite exchanges its calcium and magnesium ions that it has absorbed from hard water with sodium ions of sodium chloride solution, and thus it gets regenerated to its original form. This regenerated zeolite can be further used for the removal of hardness of water. The fourth method to remove permanent hardness of water is synthetic resin method. This method is more efficient than zeolite process. Hard water can be softened by ion exchange resins. Ion exchange resins are used to remove permanent hardness of water in synthetic resin method. There are two types of ion exchange resins. Okay, they are cation exchange resins and anion exchange resins. As their name itself suggests, cation exchange resins, what they do, they exchange their cations with the cations present in hard water. Anion exchange resins exchange their anions with the anions present in hard water. Now, cation exchange resins contain large organic molecule with acidic sulfonic acid groups. SO3H means sulfonic acid group. Okay, and this is represented by RSO3H. Here R represents the large organic molecule, that is alkyl group. Now, anion exchange resins contain large organic molecule with basic hydroxide group, usually in the form of substituted ammonium hydroxides. That is, they may be represented by the general formula RNH3 plus OH minus. Cation exchange resins can exchange their H plus ions with cations such as Ca2 plus and Mg2 plus ions present in hard water. Anion exchange resins can exchange their hydroxide ions with anions such as chloride, sulfate, bicarbonate, in other words, hydrogen carbonate, and so on, present in hard water. Okay, it is possible to regenerate an exhausted cation exchange resin bed by treating it with dilute acid solution. The exhausted anion exchange resin beds are regenerated by treating them with dilute alkali solution. Okay, now let us look at the working of cation exchange resin. In the first step, the cation exchange resin is treated with sodium chloride and is changed to RNA. Remember, cation exchange resins are represented as RSO3H. Okay, so that when treated with sodium chloride is changed to RNA. Okay, this is a simpler form, right? When compared to RSO3H, RNA is the simplest form of cation exchange resin. That is why they are exchanging it with sodium chloride. Now, in the second step, the resin exchanges Na plus ions with calcium and magnesium ions present in hard water to make the water soft. Now, when the cation exchange resin has exchanged all of its sodium ions with calcium and magnesium ions of hard water, it gets exhausted, and the exhausted resin is represented as R2M. Okay, now the resin, such an exhausted resin can be regenerated by adding aqueous sodium chloride solution. When we treat an exhausted resin with aqueous sodium chloride solution, what happens is that the exhausted resin exchanges all of its calcium and magnesium ions that it has adsorbed with the sodium ions from sodium chloride solution, and thus it gets regenerated to its original form, that is RNA form. Okay, now this is how cation exchange resin works. Now let me explain about demineralization of water. In the sense, how to remove all minerals altogether from water. Okay, first of all, what is meant by demineralized or deionized water? Water free from all soluble mineral salts is called demineralized. In other words, deionized water. That is, water free from all types of cations and anions is called a demineralized water. Now, how can we prepare a demineralized water? How is it obtained? Demineralized water is obtained by passing water successively through a cation exchange resin first, which is in the H plus form, and then through an anion exchange resin, which is in the hydroxide form. Shall we learn how to prepare demineralized, in other words, deionized water by removing all cations and anions from it in 2 steps? In the first step, the hard water sample is passed through cation exchange resin bed first. We know that the cation exchange resin bed exchanges its H plus ions, that is protons, with other cations like Na plus, Ca2 plus ions, Mg2 plus ions, and so on, which may be present in hard water. Okay, when the cation exchange resin bed has exchanged all of its H plus ions with other cations which may be present in hard water, it gets exhausted. Okay, the exhausted form of the cation exchange resin is represented as Mr2, where M stands for cations like Na plus, Ca2 plus, Mg2 plus, and so on, which are adsorbed by the cation exchange resin bed when hard water sample passed through it. Now, the exchange of H plus ions with other cations present in hard water sample results in the release of H plus ions into the water that comes out of the cation exchange resin bed. Thus, the water that comes out of the cation exchange resin bed is now acidic in nature. In the second step, water which contains H plus cations and anions like chloride ions, sulfate ions, hydrogen carbonate ions are passed through an anion exchange resin bed. We know that an anion exchange resin bed is in the form of substituted ammonium hydroxide, and it is represented as RNH3 plus OH minus. And we know that an anion exchange resin can exchange its OH minus ion with anions such as chloride ion, sulfate ion, hydrogen carbonate ions, and so on, which may be present in hard water. Now, when water containing H plus cations and anions like Cl minus, SO42 minus, HCO3 minus, and so on is passed through an anion exchange resin bed, it exchanges its OH minus ions with these anions, that is Cl minus ion, sulfate ions, hydrogen carbonate ion, and so on. Now, when the anion exchange resin has exchanged all of its OH minus ions with the anions that were present in hard water, that is, it is denoted as X minus in this reaction. X minus denotes the anions that were present in the hard water. Okay, now when what happens is that when the anion exchange resin has exchanged all of its OH minus ions with the anions that were present in hard water, it gets exhausted. The exhausted form of the anion exchange resin is represented as RNH3 plus X minus. Clear? Now this process results in OH minus ion release into the solution. The OH minus ions thus liberated neutralize the H plus ions set free during cation exchange to form water. Okay, now this is how deionized water is obtained. See, initially hard water that contained so many cations and anions were passed through the cation exchange resin first, and the cation exchange resin, what does it do? It exchanges its H plus ions with the cations that were present in the hard water, and the resulting water that is coming through the cation exchange resin consists of H plus and other anions and no cations. Now when this passes through an anion exchange resin, the anion exchange resin exchanges its OH minus ions with the anions that were present in the hard water that passed through it.
Okay, it traps the anions in the bed. Okay, so the resulting water consists of OH minus and H plus cation, and they both react to form H2O. Okay, this is how deionized water is obtained. Students, one of the most important topics of the chapter hydrogen is hydrogen economy. It deals with the perspective of using dihydrogen as a fuel for both industrial and domestic purposes. We know that coal and petroleum reserves of the world are fast depleting. So the major concern of mankind today is the search for alternative sources of energy. We know nuclear energy is there, but nuclear power has recently posed severe health and environmental problems. Even if these problems are solved, it cannot be used for running cars, ships, and flying aeroplanes. It is difficult to store or transport nuclear energy. Also, it is difficult to use it in limited amounts as and when needed. One proposed way to meet the need for new energy sources is to burn hydrogen as a fuel in industry and power plants, and possibly also in homes and motor vehicles. This proposal is referred to as hydrogen economy. There are several advantages of hydrogen economy. Firstly, dihydrogen releases large quantities of heat on combustion. It can release almost 3 times more energy than burning petrol. Burning of hydrogen in air not only liberates a large amount of energy but yields only water as the product. So, the only pollutant that will be accompanied on combustion of hydrogen is the oxide of dinitrogen due to the presence of nitrogen as impurity with hydrogen. However, we can minimize this pollutant, the formation of this pollutant, by injecting small amounts of water into the cylinder in which hydrogen is stored to lower the temperature so that reaction between oxygen and nitrogen may not occur. Okay, so how can we minimize the formation of dinitrogen oxides as pollutants when hydrogen is burnt in air? We can inject small amounts of water into the cylinder in which the hydrogen is stored in order to lower the temperature of the cylinder so that the reaction between oxygen and nitrogen may not occur, and only the reaction between hydrogen and oxygen might occur. Although usage of dihydrogen as a fuel seems to be very promising to us, there are four major barriers in achieving the goal of using hydrogen as a fuel. The first barrier is to find out a cheap method for large-scale production of hydrogen, and the second method is to find out an effective means of storing hydrogen. Hydrogen can be stored both in gaseous and liquid forms. Gaseous hydrogen, because of its bulk, is difficult to store. That is, a cylinder of compressed hydrogen weighs about 30 times as much as a tank of petrol containing the same amount of energy. However, liquid hydrogen can be stored relatively easily and safely in cryogenic tanks. Hydrogen gas can be converted into liquid state by cooling to 20 Kelvin. Okay, and storage of the same would require expensive insulated cryogenic tanks which are free from oxygen, because even if hydrogen is stored in the gaseous or liquid form, it must be kept out of contact with oxygen, because in the presence of oxygen, hydrogen forms explosive mixtures that could be disastrous. For this reason, the only alternative left is to store hydrogen in tanks made of metal alloys as interstitial hydrides like Na-Ni5, titanium hydride, magnesium hydride, and so on. These tanks made of metal alloys are in use for storage in small quantities. Hydrogen gas can then be released on mild heating of these interstitial hydrides. It is for the first time in the history of India that a pilot project using hydrogen as a fuel was launched in October 2005 for running automobiles. Initially, 5% hydrogen has been mixed with CNG for use in four-wheeler vehicles. The percentage of hydrogen would be gradually increased to reach the optimum level in the near future. It is also used in fuel cells for generation of electric power. So, what is hydrogen economy?
The proposal to use hydrogen as a non-polluting clean fuel in industry, power plants, and possibly also in homes and motor vehicles is called hydrogen economy. I repeat, it is the proposal to use hydrogen as a non-polluting clean fuel in industry, power plants, and in homes and motor vehicles. That is called hydrogen economy. And the basic principle of hydrogen economy is the transportation and storage of energy in the form of liquid or gaseous dihydrogen. Clear? This is a very important question, students. You can expect this question for sure in your exam. So, give importance to this question and learn thoroughly. I just wanted to discuss this question before I finish this chapter. How can saline hydrides remove traces of water from organic compounds? Students, do you remember saline hydrides? What are they? Binary compounds formed by hydrogen with S block elements, which are very reactive metals, are called saline hydrides. Saline hydrides are also called ionic hydrides. Examples of saline hydrides are sodium hydride, potassium hydride, calcium hydride, and so on. Okay, so when saline hydrides react with traces of water present in organic compound, they form their corresponding hydroxides with the evolution of hydrogen gas. Now look at sodium hydride. Okay, it reacts with traces of water present in organic compound and forms sodium hydroxide with the evolution of hydrogen gas. So this is how saline hydrides are used to remove traces of water, or saline hydrides are used to dry organic compounds from traces of water that might remain. Okay, so students, with this I wind up my second video on the chapter hydrogen. So all the best for your exams. Thank you for watching.